here's what's happening. Here's a phasor representation. Horizontal axis is the real part corresponding to a cosine. Vertical axis is the imaginary part corresponding to minus sine. And if we have this point right here, a real value of 1, it looks like this. This on the right is the time domain waveform specified by the frequency domain waveform on the left. And the way I want you to see what this is just imagine this thing rotating around counterclockwise. And as it rotates, you can always project how far it is along the real axis down. When it's to the left, it's negative over here. When it's 0, it's 0. And when it's to the right, it's positive. Just take a moment and realize that this projection on the horizontal axis here, on the real axis, corresponds to the amplitude of the waveform on the right.
Why would going from left to right represent the amplitude? I thought it would be kind of like similar to a wave, in which case going up and down would.
Because we're specifying it relative to the cosine component.
Oh, okay.
Remember, we're trying to map everything to cosine at a frequency with an angle, and since this horizontal axis we chose to be our cosine component, that's what's mapping to our vertical. It's somewhat arbitrary, Kyle. If we had chosen, if EEs had settled 200 years ago on mapping, on converting everything to sines instead of cosines, we'd be looking at the vertical component instead. So I want you to be able to see that since this is going to rotate up, we're going to start at a maximum, and then as it rotates up, its projection will become a minimum, and then it will become negative. So from a maximum, minimum, and negative. Watch what happens if we start over here. Now this phasor, which is both here's a phasor which is plus cosine minus 1 times sine. It will start with an angle that's not 0. In other words, its horizontal projection will not be at its maximum. It'll reach its maximum later on. It will, as this thing moves to the right, its projection will decreases, then becomes a negative maximum, which it does down here, and eventually become a positive maximum higher than when it started. And the point that I want to make is that this red animation is showing you how to recreate the time waveform in your mind from the phasor representation, but we're representing this entire waveform just with a single complex number. So, Bobby, if we move this over to, say, this vertical axis, can you tell me intuitively where this will start and where it will move?
Would it start at 0?
It'll start at 0, and if we move it up here, where will it go? Will it go downwards or will it go upwards?
Downwards.
Yeah, that's it exactly. And no matter how high or low, it'll always start at 0. But what we impact is how high or low it goes later. Who have I not called on? Pavel, where would I place this phasor in order to get something that doesn't go down, but instead starts at 0 and goes up?
At negative 1 on the x-axis.
At negative 1 on the y-axis.
Oh, yeah.
And now when we start moving it, it'll start going positive. So negative 1, remember this corresponds to a b of positive 1. So this would correspond to a b of negative 1, which corresponds to a plus sign. And that's what you're seeing over here is this plus sign. Jesse, how about what would happen if we moved this phasor and made it, instead of negative j, which is what it is now, we made it negative 1. Describe to me what we'd see in the time domain over here on the right. We're going to move this phasor to a negative 1. Where will it start And where will it go?
It would start at the minimum and then
Exactly.
start going up.
That's it exactly, right over there. And you can see how in general, as we move this starting phasor anywhere in the complex plane, we can get any sinusoid at all. And so we've replaced the infinite number of points in the time domain with just this one complex number. And this is called two different things. This is called the complex plane, which makes sense. It's also called the frequency domain. And so we've got this one point in the frequency domain representing this entire waveform. This point is called the phasor representation of this waveform. Any questions about that? Okay. That is the intuition with what we're doing. And that intuition is not, I think is not a straightforward one. Everything else in today's class will go down easy if you understand that.